Hi everyone, my name is Zaeem and welcome to my takeaway. Today I will be talking all about computer graphics and the technology that powers all of our favorite video games and animated movies. To start off, let's try and understand what exactly is rendering. So, if you were to develop a video game or an animated movie, you would typically create a virtual world that holds all the models, animations, textures, lights, and other objects that makes up scenes in your game or movie. In the case of 3D games and movies, those models would of course be 3D, right? But as we know, our computers, monitors, and televisions have 2D screens. They are just rectangular grids made up of little squares called pixels, and each pixel can only have one color. So rendering in the context of computer graphics is essentially how do we take all of the scene information that you may have defined in 3D and generate the final 2D image that we see on our screens. So one way to do that is what's called rasterization. So when it comes down to it, the surfaces of all the objects in our scene are made up of primitives, such as lines, triangles, circles, and polygons. In fact, the surface of every 3D object in our scene can be approximated by a whole bunch of triangles. Even the surface of a sphere can be approximated by just triangles. So what rasterization does is we go through all the triangles in our scene, we see which pixels each triangle overlaps, and we then project the triangles onto their pixels accordingly. But because a scene in a movie or a video game is shot from just one point of view, the viewer's point of view, some objects may be behind other objects in the viewer's line of sight, and so some triangles will overlap each other in our 2D screen space. And so, depending on the order in which we draw these triangles, some triangles will either need to be drawn over overlapping triangles if they are in front of what's already been drawn, or they need to be discarded if they are behind what's already been drawn. Now, you might be thinking that since there are like a gazillion triangles in just one digital scene, how the heck can we process all these triangles every single frame? Well, it turns out that GPUs can do this quite quickly, taking advantage of things like parallel processing and cache memory to do rasterization quickly, and hence it has been the go-to method in video games and animated movies for decades. However, a limitation with rasterization is that because it simply draws objects onto the screen, it doesn't take into account effects like lighting, reflections, and shadows. We have to add in those things afterwards or as a separate step. And the methods of adding those things in are generally complex and unintuitive, and are merely hacky ways to mimic these effects. So for example, to render reflections such as a mirror or maybe a lake, you can do what is called a planar reflection, which is to treat the mirror as a camera and render the entire scene from the point of view of the mirror, and then smack that rendered image onto the mirror. Now, that may work, but you're essentially rendering an entire extra scene per frame, which slows down computation. Another option is to use screen space reflections, which is faster, but only reflects objects that fall on your screen, and doesn't take into account anything that falls off your screen, so it's not as accurate. And what about shadows? So one popular method is to use shadow maps, in which we render the scene from the point of view of each light source, and then we can kind of shine light on all the visible objects in the light source's point of view and leave the rest of the objects unlit. But now you're all of a sudden rendering multiple scenes per frame, one for each light source, which slows down computation even more. Another option that is commonly used is to basically render all the lighting and shadows beforehand and then bake them into your assets. Now, this can work, sure, but that will impact memory and the file size of your game, because now your assets would have to store all of this extra lighting information all the time. Also, this option only really works for non-moving objects in your scene. For any object that can move or is dynamic in any way, baking is not really an option. And then if you want transparent objects in your scene, such as a glass of water, well, because of how rasterization works, you have to draw the objects from back to front, hence waste time on sorting. And so, it is rather difficult and unintuitive to render realistic images with rasterization, just because of the nature of how it works. Now, let's look at another rendering technique called ray tracing. But before that, let's have a look at how we can actually see things in the real world. So, imagine a very simplistic world which has a light bulb, an apple, and yourself, the viewer. Now what will happen is that the light bulb will emit rays of light out into the world in an infinite number of directions. Some of those rays may hit a point on the apple. Since an apple is a diffuse object, some of those light rays will be absorbed, while others will be redirected in a number of directions. Some of those redirected rays may hit your eyes, and that's how you'd be able to see that point on the apple. So we want to simulate this for 3D graphics. But if we were to go and simulate all the infinitely many rays, it would be computationally insane, right? But hang on a second, we don't actually care about most of these rays. We only really care about the ones that actually reach the viewer, or the player if it's a video game. So in this scene here, we only really care about the dotted rays shown. So how about, instead of simulating all of these rays, how about we instead shoot rays backwards from the viewer, see what objects the rays hit, and then trace those rays back to the light sources that it started from. So that's exactly what ray tracing tries to do. We shoot a virtual ray of light through each pixel on our screen and see what it hits. Once it hits an object or a point in our 3D world, we can do a bunch of things. So let's start with shadows. Know where the light sources are in our scene. So we can shoot a secondary ray from the intersection point to the light source. This is what's called a shadow ray. So if the shadow ray hits something along the way to the light source, that means that another object is blocking the light from hitting this point. And so we know that we should cast a shadow on this point. If the shadow ray doesn't hit anything along the way to the light source, no shadow. So yeah, shadows sorted. What about reflection? Well, if we have a mirror in our scene, and if our first ray hits the mirror, and if it is a true mirror, we know from mathematics that the angle of incidence is equal to the angle of reflection, and so we'll know which direction to shoot the reflected ray off to. The reflected ray may hit another object, and we can then set the color of the mirror accordingly in its pixels. And lastly, if our first ray hits something like a glass of water, we can spawn an additional ray when it enters the glass of water and another ray when it exits it. Again, this can all be computed using linear algebra. So that's the basics of ray tracing, and we've essentially achieved shadows, reflections, and transparency in a much more intuitive and convenient way compared to those hacky ways which we had to do with rasterization. Now, let's look into some more advanced forms of ray tracing. The first is called distributed ray tracing. So this is the same as classical ray tracing, but instead of shooting just one shadow ray, for example, we shoot a burst of shadow rays. Because if we were to shoot just one shadow ray, we would get very pure, hard shadows all the time. But hard shadows are not always the most realistic. So in this diagram here, we shoot one ray from our viewer into the scene as usual. It hits an object. Awesome. Now we shoot 3 shadow rays to arbitrary points on our area light source. We see that 2 of the rays hit the light source and 1 gets blocked. So we can say, well, okay, 2/3 of that point on our box should be illuminated, and we can do a softer shadow on it. We can do a similar thing for reflection rays. So instead of shooting just one pure reflected ray, we can shoot multiple rays about the true reflection. So if an object is not a pure mirror or has a rough or rounded surface, by shooting multiple reflection rays, we can achieve a softer or fuzzier reflection on an object. Another cool thing that we can do with distributed ray tracing is motion blur, which we can achieve by shooting rays over a number of frames.
So ray tracing is awesome, but there's some things that it can't handle. One of which is that it assumes that light is always coming directly from a light source. But in the real world, that's not always true. Light can also bounce off other objects before hitting the object that you are looking at, in what is called indirect lighting. So in this image here, we have a spotlight which shines some light in a circle on the ground. But then what happens is that some of that light bounces off the ground and hits surrounding surfaces, and then bounces back onto the floor surrounding the spotlight. So this is a step towards what's called global illumination, and is one of the hardest problems in 3D graphics. And here we have a scene with some boxes, and we can see that the sides of the boxes are somewhat tinted red or green because of light bouncing off to the walls and onto the boxes. So this is what's called color bleeding, and is another example of global illumination. So one way that we can approximate global illumination is through path tracing. So path tracing can be thought of as an extension to ray tracing. So just like ray tracing, we shoot virtual rays of light through every pixel in our screen and see what they hit. But unlike ray tracing, we don't just stop after hitting the first object. Instead, we follow those rays along a series of reflections and redirections until we reach a light source, hence tracing the full path of the rays.
So here we have a scene which has a light bulb, a bunch of objects, and our viewer. So as with ray tracing, we first shoot a ray of light from our viewer into the scene, it hits an object. We then shoot a ray of light from our object to our light source. That will be our direct lighting. Now, as for indirect lighting, we don't really know where the light is coming from. I mean, light could be coming from all sorts of directions. So, we shoot a bunch of rays in the random directions and see what happens. So a secondary path might hit the first object, hit the ground, and go off into the sky. So now that path will never ever make it to the light source, so we can just ignore it. Another path might hit the first object, the second object, and then hit the light source. And the color of that path will be the combination of the colors of the first object, the second object, and the emission of the light source. Another time we may not be so lucky, and the ray hits both objects and goes off into the sky. Again, we can just ignore that path. Another path could hit all three objects before making it to the light source, and all three objects would contribute to the color of that path. We keep on shooting paths randomly like this. Once we've traced all the paths possible, and by that I mean once we're tired of shooting rays, we look at all the paths that made it to the light source. So in this case, that will be the purple ray, the green ray, and the blue ray, and we sum them all up, and that will be the color for the pixel in question. So because we're tracing all these paths at random directions all the time, we need to path trace lots and lots of rays per pixel, like hundreds if not thousands of rays per pixel, in order to get a good answer. And so path tracing is very computationally expensive. But it can be shown that the more rays that we sample at each intersection point, the closer we will get to achieving true realism in 3D graphics.
So here's a scene that was shot with ray tracing, which showcases all the things that we talked about. We can see that ray tracing achieved transparency in the glasses, as well as specular, soft reflections on some of them. Now, the scene was rendered way back in 2006, which was quite a while ago, especially in a field like computer graphics. Let me show you what a more recent path trace scene can look like. Insane, right? The first time I looked at this image, I thought it was a real image and not a rendered image. Insane. And this here is a scene from Star Wars that was rendered entirely with ray tracing as part of a demo by NVIDIA. Now, what's important to note is that ray tracing is not new, right? It's an algorithm that was proposed back in the 1980s. We just didn't have the hardware and resources to do ray tracing practically until now. So let's see some of the areas where ray tracing has been used in practical use. The first of which are animated films. So Pixar have been using the Ray's algorithm in their in-house renderer, which they named Renderman. Initially, Renderman had ray tracing and global illumination as added optional effects. But in 2016, Renderman was completely re-engineered to use Monte Carlo ray tracing as its primary rendering technique. And it has since been used for a lot of their movies, including Finding Dory, Cars 3, and Toy Story 4. And Disney's Hyperion renderer has also switched to using path tracing and global illumination to produce their film. They also use some smart optimization practices in which they group multiple rays together according to the direction that they're going. And because the rays in the group will most likely hit the same object in space, they can optimize calculations for those object hits. And these sort of optimizations allow the renderer to handle several million rays at a time. And this renderer has been used to produce lots of their movies, including Frozen 2 and Big Hero 6. Now, path tracing for movies is possible because movies are pre-rendered, right? And so the producers have ample time to path trace thousands of rays per pixel without needing to worry too much about how long it takes. For example, it's reported that it took 83 hours on average to render a single frame of Big Hero 6. But video games are not pre-rendered. It all happens in real time.
And we can't be waiting 83 hours for a single frame in a video game. Heck, in this day and age, we want 60 frames per second, otherwise the game is trash, right? So the question now is, how do we do ray tracing and all these advanced forms of rendering in real time and while still maintaining current performance standards? Well, one answer to that is, of course, better hardware. So, traditional GPUs such as NVIDIA's Pascal GPUs are optimized to do rasterization, but aren't very optimized to do ray tracing. So, NVIDIA went and built the RTX series of GPUs based on the Turing architecture, and which adds two things: tensor cores that are optimized for AI and deep learning, and RT cores that are optimized for real-time ray tracing. AMD have also built their own GPUs that are optimized for ray tracing. However, while NVIDIA have already released 3 iterations of RTX GPUs at the time of recording, AMD are still in their first iteration. So the results on their GPUs aren't on par with NVIDIA yet, but they still produce very good results. It's also the same architecture that's used to power the visuals for the PlayStation 5 and Xbox Series X. However, an issue with path tracing is that because we're shooting rays at random directions all the time, the rendered image tends to be quite noisy. But the more rays that we sample per pixel, the less noisy the image gets. But for real-time applications like video games, we often cannot sample that many rays per pixel. And so while we want to do fancy stuff like ray tracing in real time, the reality is that we often end up with quite noisy images. So how do we solve that issue? One word: denoisers. This is a software that takes in noisy images and, well, denoises them. So this here is a sample result of a real-time denoiser developed by some researchers. On the left is an image that was rendered with just 2 ray samples per pixel, and on the right is the result after applying their denoiser. So NVIDIA, AMD, and Intel have all developed real-time denoisers for ray tracing. There's also some denoisers that use machine learning, which can produce especially good results. Denoisers are also useful if you want to do ray tracing, but instead of shooting a ray through every single pixel in your screen, you can shoot a ray through every second pixel in your screen, for example, for faster rendering. What you then get is a whole lot of blank pixels throughout your image, which can then be covered up with a denoiser. Another hurdle is that our screens tend to be high resolution, with HD being the standard for laptops and monitors, and nowadays even 4K is becoming more and more a thing. Because ray tracing works on a pixel by pixel basis, the higher the resolution of our screens, the more rays we have to shoot, and the longer our rendering takes. So NVIDIA went and said, hey, what if instead of doing ray tracing on an HD image or a 4K image, what if we could do all of our rendering on smaller sized images, and then train a deep learning AI model to upscale those rendered images afterwards to a higher resolution, such as HD or 4K, in real time? Well, that's exactly what they did, and they call this piece of software Deep Learning Supersampling, or DLSS for short. And because rendering at a lower resolution is so much faster, it helps us achieve two things. So it firstly creates more time for us to do advanced rendering techniques, such as ray tracing, in real time. And secondly, we get significant boost to frame rate. So at the time of recording this talk, NVIDIA have 2 versions of DLSS released. So DLSS 1 used an upsampling neural network, but it was quite limited in that it had to be retrained for every game. DLSS 2 solved this limitation by using a network that recovers data from previous frames, and so it does not need to be retrained for every game. AMD also developed their own similar image upscaling software called Fidelity FX Super Resolution, or FSR for short. But unlike DLSS, FSR uses open source methods instead of deep learning, and so it doesn't need any training data or frame history to work. Also, FSR is not limited to recent graphics cards, unlike DLSS. However, both solutions can upscale an image by 4 times its original resolution in real time. So here are some screenshots from a game called Control, and on the left is what Control looks like without ray tracing, and on the right is what Control looks like with ray tracing. And we can see that the ray trace version on the right has better reflections of light on the floor, and it just stands out a lot more. And here is what Marvel's Spider-Man looks like with and without ray tracing, and we can again see that the ray trace version on the right has better reflections on the floor, and the lighting just looks better overall. And here are some screenshots from Watch Dogs Legion, and again we can see that the ray trace version on the right has better reflections of light on the floor, and the lighting just looks better throughout the whole scene. And here is what Minecraft looks like with and without ray tracing. Now, at the time of recording this talk, NVIDIA very recently announced their next iteration of RTX GPUs, and I would love to share a little about some of the cool things that got announced. So the RTX 40 GPUs will adopt a new architecture called Ada Lovelace, and it will add more RT cores and tensor cores for faster rendering. And in addition to that, they also announced the next evolution of DLSS. So what DLSS 3 will do is that in addition to allowing us to render at lower resolutions and upscale in real time, it also adds a new thing called optical multi-frame generation. So this software can actually generate entire frames of a video game in real time. So the way that it works is that it looks at two successive frames in the game and studies the movement between them and uses that to predict or generate the next frame in the sequence. So yeah, we literally have AI that can generate frames of a game in real time. And this allows us to achieve tremendous frame rate boosts. And this is all in real time and with ray tracing turned on. NVIDIA claims that with the help of DLSS 3, we can do path tracing in real time. Now, whether that's true or not, we'll have to wait and see. Another cool thing that has come out of NVIDIA's conference is a modding tool called RTX Remix. So this modding tool uses AI and DLSS to enhance in-game assets and effectively turn any game ray traced. It's currently being used to apply ray tracing to older games like The Witcher 3 and also more classical games like Portal and Quake. So as an example, on the left here is a screenshot from Portal, which released 15 years ago, and on the right is what Portal looks like after applying RTX Remix. And on the right here is a screenshot from The Elder Scrolls Morrowind, which is a 20-year-old game. And on the left is what Morrowind looks like after applying RTX Remix. So RTX Remix is really just a great way to give new life into our much beloved classical games and get to experience them again with modern lighting and rendering techniques. The last thing that we're going to look at is Unreal Engine 5. So Unreal Engine 5 uses a software called Lumen, which applies ray tracing and global illumination that is more software focused and is less dependent on the hardware. Essentially, software ray tracing. So the way that it works is that it applies 3 different methods to compute lighting for a scene. The first of which is called screen space ray tracing, which applies ray tracing to objects that are visible on the screen to the viewer, but doesn't know anything about objects that fall off the screen. It also does a form of voxel-based global illumination, which basically slices up the world into boxes and then ray traces against those. So that's able to quickly produce a rough approximation of lighting the entire world, including things off the screen. And then virtual shadow maps adds in a final layer of detail, but over a smaller area of the world. Basically, just the stuff nearby the camera or on the screen. Now, all these methods are limited forms of ray tracing on their own, but because each form is strong where others are weak, when combined together, you get something that looks like full-blown, pixel-exact ray tracing, with a much less performance cost. Let's see some results. So this is a screenshot from Unreal Engine 5's first announcement in 2020, which showcased a game running in real time on the engine. I recommend checking this out if you haven't already. This rendered scene showcases the engine's ability to capture lighting and reflective surfaces. This model of a car rendered by the engine showcases its ability to capture transparent objects, such as the windows of the car. And this is a screenshot captured from my PS5 of The Matrix Awakens, which is a small open-world demo game built using the engine.
So these are some resources that I would recommend if you'd like to learn more about graphics and ray tracing. And that's all from my takeaway. I hope that you all enjoyed it. I am always open to questions, discussions, nerdy conversations about this stuff, anytime, any place.